From previous lecture, we have already known that for a key nearest neighbor algorithm, if we just take the simple key nearest neighbor algorithm, so its time complexity is order of n. We have already know, and it will happen if our d and k is small. If d is small as well as k is small. Okay, we have already seen this thing, and also its space complexity is order of n. So this is time complexity and this is for space complexity, both are the same. If we use simple k nearest neighbor algorithm, if we just take the simple k nearest neighbor algorithms, then we have seen this thing. Now we are interesting is how to apply some technique here that our time complexity we can reduce easily. So we are now interested to reduce the time complexity. We have seen or in a simple kn in our time complexity is order of n, and now we are interested to reduce from order of n to order of log n. So let's see how we will reduce this complexity. So just take the advantage of, if we simple just take the log of order time complexity order of log n, then how much time we will easily reduce. Suppose let's take we have n is equals to 1024. If n is equals to 1 of 0, simple, if you take the logarithms of this one, it will be 10. You can see from where to where we can easily reduce our time. From 1024 to we can easily reduce to simple 10 by using. Now we are interested how to reduce this time complexity from order of n to order of log n. The simple concept is here we are using instead of using kn and simple kn, we are using here kd tree NNN algorithm. Just here we are applying the kd tree NNN algorithm. So let's see how this thing is actually doing in KNN. So before knowing this concept KD tree, we are interested to discuss some primary concept of binary search tree. Okay, so let's see what is actually a binary search tree. So binary search tree is nothing, just KD tree is nothing, just simple extensions from the binary search tree. So let's see first what is binary search. If you understand a binary search tree, then I think you will easily understand the KD tree. So first see what is actually binary search tree. Or in short we can call BST, binary search tree or BST. So this is simple. First it is a data structure algorithms to search a number from a data structure. So this is a first simple, it is a data structure, and the second one, its main thing is it's a binary search. It is searching algorithm, yeah, search algorithm. Okay, and so let's see one by one. The problem is our main problem, or actually I think before going discuss the before going to the solutions, it is better to understand the problem first. So our problem is actually, so we have a given sorted array, and we have to find a number, it is present in that array or not. Our problem is that actually our problem is we have given a sorted array. Okay, and we are interested to find a number, it is present in this array or not. Okay, this is our main problem. Now we are, so let's solutions, how actually we are done this job by simple using the complexity. So if you just take the linear search technique, if you just remember, you remember the linear search technique. So first I think it will be better if we just consider a problem corresponding consider an example corresponding to this problem, then I think it will be easily understandable. So let's take our array is like that. Suppose let's take our, here I am taking the size 8 array. Suppose let's take, I think it will always better if we consider a small example. So suppose let's take 1 2 3 4 5 6 7 8. So first number, second number, third number, fourth number, fifth number, sixth, seventh and eighth. Let's, our first number is 1, second number is 2, third is 6, fourth one is 8, sixth one is 12, fifth one is, sixth one is 15. Let's take seventh is 17, 18. Let's take, these are the a number of, that is a sorted number. We have easily see this is sorted number, and this is the corresponding index of our array. So this array is simply a sorted array. This is a simple sorted array. Okay, first our task is, our first job is construct a binary search tree. This is our first job. We have to interest to construct a binary search tree. Okay, so let's see. So first what we are doing here, we have to find, first we have to find the median of the whole the element, of whole the element. Whole the elements means the element of our given array, that is sorted array. So what will be the minimum of this given sorted array? So you have see that, you will see that here we have 8 elements. So our middle element will be 4 and 5, because it is a even number. So middle one will be n by 2 and n by 2 plus 1 middle number. So median will be here, if n is equals to even, then it will be n by 2 and n by 2 plus 1. If n is equals to odd, then then this number will be what, n plus 1 by 2. I think we have already know this thing. Okay, so what will be here, n is equals to even means 8. So this this n by 2, n by 2 means what, 4, and n by 2 means 5, corresponding to mean of these two will be our actual median of this sorted array. So what will be the median? Just if you just write this thing this way, so the median of this thing is 10, means simple average of these two numbers, average of 8 and 12 is 10, simple. So first we have to write this thing 10. First we have to take the median of whole the number. Okay, 10. Now to construct a tree like that, now we construct this tree like that, 10. And now we have using a decisions here. Here decisions means this, now this number, if a number is any number is less than of 10 or not, means it will be better if I use this symbol. It any number is less than is equals to 10 or not. Okay, we have to check these decisions here. If yes, we will send this number that way. If no, we will send this number that way. Okay, I have understood. I think you have understand this thing. Okay, first we have pick the median of the whole number of the whole array. Pick the median of the whole the array, and just take the conditions. If you're interested, you can get at that sign. So then the yes root will be here and no will be here. So just I am an example I am using here, less than equals to. If it is less than equals to 10, then I am going in these directions. If it is no, I am going in this. So the next thing is the all the element, it is the sorted array, all the element less than is equals to 10 this side, and all the element greater than is equals to 10 in side. So just now we are doing the same thing, repeat from this side as well as this side. Okay, now I am here using another color. Okay, so just see the first left side. So what will be the median? So here actually we have 4 element, median will be 2 and 6, 2 and 3 median element. So now in the left side our median will be 2 plus 6 by 2, mean of these two number, that is 4. Okay, and this side median will be the same, 4 number, median here will be 15 plus 17 by 2, means 15 plus 17 by 2, it will be 16. So here we are doing this. So now 4 less than is equals to 4 or 16, it is less than is equals to 16. We have doing this job this side. If less than is equals to 4, then we are sending this element these directions. If no, we are sending this element this direction. Similarly as well here. If this less than is equals to 16, then we have sent this element these directions. If no, we have sending this element this direction. Now let's see. So less than is equals to 6, 4 less than, so just say less than is equals to 4, which element? 1 and 2, 1 and 2. Now we are find the, now I'm changing the another color. I am changing here this color. Now just median of these two means what? Here median will be 1 point. Similarly here, what is the median of these two number? It will be 17.5. So here now we are interested to find the left element. Yes means median will be 1.5. The same thing also I'm repeating. 1.5. Yes, no. So which elements are 1, and if greater than equals to then 2. So what the thing will be happen here? So 1 means they have nothing element, just only rest of the 1 element. Yeah. We have written here 1, and here we written 2. Now we are reaching only single element. We have no we don't find the median element of this 1 and 2. This will be the single. So now we will break this loop here. We will stop this processing here. Now just see. Now just see here. Now we are go back here and construct the no this thing. So now we are interested to find the no which are bigger than 4, larger than 4. So what will be the 6 and 8? So just 6, and if you just see the what will be the median of 6 and 8? What will be the median of this 6 and 8? 7.5. Okay, so what will the median of 6 and 8? So median of this 6 and 8 is 7.5. Here now will be 7.5. We are inserting the similarly checking conditions. If a number is less than 7.5, then we have send this side. If we have greater than, then we have sent this side. So let's see. 7.5 is less than 7.5, only have 6 element, 1 6, and no 8. Now we are reaching the 1 element, we have stopped. Now the same thing. Now 16, come to the 16 part. 16, what will be the yes? Now come to the yes part. Now what would be the 16? Less than, first less than 16. So what will be the less than 16? 12 and 15. So 12 and 15. So now we have find the median of these two numbers, 12 and 15. What will be the median? And 12 and 15, 13.5. 13.5. Okay. Yes, 13.5. 13.5. Now here we are interested to 13.5 less than is equals to checking condition. Yes, no. If yes 13.5, what will be the element? 12. If no, what will be the element? 15. We have only one element here, so only one element, don't interest to break. Now let's do the 16. Greater than is equals to 6. Greater than is equals to 6. Means 17 and 18. So what would be the median here? So here median will be, I have taken another thing, this color. 16, the median element 17 and 18, 17.5. It will be similarly divided in two groups. Less than checking conditions also. Yes or no? So if yes, what will be the, if less than yes, then what will be the number here? 70. If no, what will be the number here? 80. Okay, I think you have understand. This is simple binary structure of this sorted. Now we will see if we just implement here. Now we will see if we just implement here. Suppose we are interested to find a number, we have to find an element from this array. We are simple element. We had simple interest to find the element by through a linear search. Linear search. If we just simply linear search, the order will be what? Order will be order of n, means we have to compare each element one by one. We have to compare one each element one by one. But here if we using simple the binary search tree to find this element, suppose we are interested to find the element, suppose let's take 15, then interest to find the position element 15 from this sorted array. So here we will see this time complexity will reduce to order of log n by using simple binary search tree. This structure, binary search tree data structure. Okay, so let's see how. So suppose what power first, this actually we there have some name. This structure is called the root node. This node is called the root node. Okay, root node. And this node, the end of the every in the end of the structures, this node is called the leaf node. This node is called the leaf node. Okay, A1 is the leaf node. 1 2 6 8 12 15 17 18. Is node is called the leaf node. I think I have done some mistakes. No 1 2 3 4 5 6 7 8. Okay, I have not. Okay, and this element, this thing, this is called the depth of the DST. This thing, this is simple called the depth of the DST depth. So how much here depth? This is the 1 2 3. So here depth is what? Depth is 3. Means 1 root, 2 root, 3 root. To leave to actual depth means to how much root we have to compute, how much root we have to overcome to reach from root node to leaf node. This is the simple depth. So just we have taken here, root node is what, 10, our leaf node is what, 1. So we are, if you just reaching from 1, so root node to leaf node, the shortest route is this one, this one, this one. So by through shortest route we have reaching to a leaf node by simple, we have to overcome three routes, three route. So the depth is actual 3 here. Okay, I think you have understand. This is the depth, this is simple called the depth. And this is the root node. Root node means its depth is simple 0. Do the root node, the simple in root node the depth is 0, this depth is 1, this depth is 2, and the depth is 3. Okay, this is called the depth of the root, depth of the. So let's see how we'll search. Suppose let's say we are interested to finding a element 15. So first we are comparing 15 is less than or greater than 10. Yes, obviously it is greater than 10. We have take this route. We are interested to find a element 15. We are interested to find 15. Okay, just I am using to this thing to pink color. Just follow this thing. So we are interested to find 15 to this BST. So first compare to 10, yes or no. 10 is less than 15 or no. No, 15 is greater than 10. So we have maintained, we have taken this route. We have tracked this route. 10. Okay, we have tracked. Now we are comparing 16 to 16. So 15 is greater than or 6 or less than. Yes, obviously 15 is less than 16. So now we are coming this route. Now we are comparing here. So first what comparing? First we are comparing here. Second we are comparing here. Now here 13.5. 15 is greater than or less than 13.5. Yes, obviously greater than. So now we are taking this route. So here we have comparing 3. First, second, third. Just we are consider. Just I am coming here. Okay, I have reached my targeted element. So just if you see, we have only compared 3 elements. First 10, then 16, then 13.5. Only by comparing 3 elements we can easily find the 15 element. But in linear search we have to compare each element. So this is the main advantage of the BST. We can simply reduce the time from order of n to order of log n. This is the simple. I think you will understand this thing. So in BST, time complexity to search element is order of log n. Because why? Actually here in binary search tree we have, suppose here we have 8 elements. Okay, in 8 element we have compared, we have 8 element. Okay, we have element to, in BST we have comparing how much? Only 3 elements. Only 3 elements in BST. Okay, so if you just apply here logarithm log of 8 is simple 3. Okay, this is the same. This is for this. So in BST time complexity to search element is order of log 8. So in BST time complexity to search element is order of log n. And one thing, just if you one thing, we have the depth is what? Here we have 8 elements. So for this tree we have constructed BST. The depth is what? 1 0 1 2 3. So 3. So the simple thing, if we have n elements, the depth of the BST is also order of log. Okay. So I think the simple thing is, for a BST, the time complexity is simple. The depth of this BST, depth of the binary search tree is simple. The time complexity by using same thing in KNN, in KD tree, just in the Next lecture we will see, by using simple this binary search tree concept, how we will construct the KD tree. Okay, so I think the how this time complexity is reduced to n to order of log n, I think you will understand this thing. I suggest you to understanding this thing is betterly, if you choose first, if you choose n is equals to 4 and any sorted number by n is equals to 4, you have choose and construct a binary. So this binary tree will be like that. In leaf node we have only 4 elements. If we choose n is equals to, just multiply of 2 power, so here 2 square, here 2 cube. Okay, here depth will be what, 3, that we already see in the previous example. If we choose n is equals to, suppose let's take 32 and say 2 power 5, suppose let's take 5. So in the root node it will be also 32 elements. So what will be a depth? 1. Here if we have 80 elements, so depth will be here 3. Here depth is 2. Just see this now. Just see this now. So for n is equals to 32, what will be the such depth? So in such cases depth will be 5. I think you will understand this thing betterly by through this example, how a binary search tree is simple constructed, and how we can easily reduce the time, comparison time to n to log n by example using this data structure.